Okay, so at the end of our last class, we looked at an example where we had a silver nitrate solution mixed with ammonia. And so that silver nitrate solution, the silver nitrate dissociates, but it dissociates completely. And we saw what amount of each of those species, silver ion, ammonia, silver with one ammonia ligand attached to it, and silver with two ammonia ligands attached to it. And so we looked at that from the standpoint of how much of each of those are there, and we went through that calculation. And that was starting with silver nitrate. But this, the formation constants associated with adding one or two ammonia molecules respectively to the silver can have an effect on the solubility of something like a silver chloride, which we know is not very soluble. And so as we move forward, just I want us to start thinking about how our last example is related to say, well, what happens if we make a change, right? What if we start, instead of with silver nitrate, what if we start with silver chloride? So silver nitrate, we know, has a very large KSP, right? It's very soluble, right? And that's because of the nitrate as the anion for that ionic substance. But the KSP for silver chloride, very small. And so what we're going to do towards the end, we're going to just do a quick calculation of the solubility of silver chloride, just as for the sake of comparison. But what happens here is, if you have silver chloride in a solution, its solubility will be affected by the presence of the ammonia, right? Because those formation constants for when you add ammonia to the silver nitrate, right? Those formation constants where you have that silver ion will come into play here. And so what happens is, essentially, when you utilize, right, the ammonia, well, you're using up this silver ion, which means you're pulling this reaction over to the right. And so the example that I want us to go to and look at will be looking at solubility of something like silver chloride in an ammonia solution, okay? So to determine the solubility of something like silver chloride in a solution that already has ammonia in it, we can basically look at all three of those equations that are at play. We've got the solubility of the silver chloride, the first formation constant, and the second formation constant. And if we put those together, remembering that generally the concentrations of the ligand are very high, so it really pulls those second two equilibria very far to the right, then we can add these together, right? We add our products to the product side and reactants to the reactant side, like we always do when we combine equations, and you wind up with an overall equation that looks like this. And this has some similarity to the solubility. Namely, you have silver chloride over on the reactant side, right over here. And then you have chloride. And now, though, the big difference is you now have this silver ammonia complex that you have to account for. But if you look at the equilibrium constant for that whole thing, you can determine that just by the reaction, at least the expression for it. So that expression, remember, is just the silver ammonia complex times the chloride complex concentrations divided by the ammonia concentration squared. And you get that if we just added those equations up. Remember, we multiply those equilibrium constants like we did back, way back in chapter, what was that? Chapter 14, right? 13, excuse me. Chapter 13, we did that. And so you wind up with an overall equilibrium constant for that expression up there, the circled one, right? That is, the equilibrium constant is just the product of the three equilibrium constants we looked at above. And so what that allows us to do now is say, okay, well, what is the solubility of silver chloride in an ammonia solution? In this case, we're going to say in a 10 molar ammonia solution. And you can look at this as being, well, the solubility is just going to be based on how much of this silver chloride dissolves. And so to do that, the easiest way to set this up is actually to set up an icebox. And so we'll do that icebox with the overall equation that we had on the previous page. So silver chloride, solid, plus 2 ammonia aqueous, reacts to form silver complex ion with ammonia. That's aqueous plus chloride ion. So we're going to use that equation on an icebox to set this up to really see how our calculation goes. Now we don't have to take into account the silver chloride because it's a solid, so we can just put our, hold on. So we don't have to take into account the silver chloride solid because it's still a solid, so it's not part of the equilibrium constant expression. We know that our equilibrium constant expression, K, will equal the concentration of chloride times the concentration of silver ammonia complex divided by the concentration of ammonia squared, and that we're going to get from the previous page, the combined equilibrium constant, the 2.8 times 10 to the minus 3. Okay. So our initial concentration of ammonia, we said, okay, well, this is a 10 molar ammonia solution. So we'll say that's 10.0. And initially, we're not going to have any of our complex ion or the chloride because before it dissociates, you don't have any. And so when this dissociates, we make, for every one silver chloride that dissociates, we make one of the silver ammonia complexes and one chloride. So we'll call those plus X. And we lose 2 ammonias because it's the stoichiometric ratio. So minus 2X there. And so at equilibrium, you would have 10.0 minus 2X. And for the silver complex, you'd have X. And for the chloride, you would have X. And so what we can do now is just plug it into our equilibrium constant expression of 2.8 times 10 to the minus 3 is equal to, well, here we've got X squared, because the chloride and the complex ion concentration, all of that divided by 10.0 minus 2X. Make that clearer. There. Minus 2X, that quantity squared, okay? And so there's a nice little trick that you can do for something like this, and it doesn't always work out math-wise, but this one happens to be a great one for us, is that we can basically just go, and I'm gonna change my color to see so you can really see it. The nice thing is, since we have a square in the numerator, right up here, that's squared, and in the denominator there, that's squared, we can just square root this entire thing to make our lives a heck of a lot easier. And so what that leaves us with now is the square root of 2.8 times 10 to the minus 3 is equal to X over 10.0 minus 2X. Okay, and so that makes our lives easier. That if we just take the square root of 2.8 times 10 to the minus 3, we wind up with 0.0529, right? That's just this right there, okay? And so we can multiply each side by 10 minus 2x, and so you wind up with 0.529 minus 2 times that, so 0.1058x is equal to x. And so you can say 0.529 is equal to 1.1058x. Divide each side by 1.1058. Okay, and so x winds up being 0.0479, okay, which means that our concentration of the silver chloride is 0.0479 molar. And we can get that because X is how much chloride dissolves, which is going to be the same as the solubility of silver chloride. And so that's our overall answer for the solubility. You get 0.0479 molar silver chloride. And so sort of to think about that in perspective of, with the perspective of how soluble silver chloride is by itself, right? You could look at the molar solubility of silver chloride in water. Okay, so all you do there, because silver chloride dissociates to give you silver ion plus chloride ion, right? Well, you know, KSP will equal the concentration of silver times the concentration of chloride, right? So essentially, without putting the full icebox together, your KSP, which you can actually go up here to get 1.6 times 10 to the minus 10 for the chloride solid dissociating into silver ion and chloride ion. And so that right there would be 1.6 times 10 to the minus 10. And we could say, well, based on our solubility ice tables in the past, that would be equal to x squared because the concentration of silver ion and chloride ion will be the same. And so you could find that the concentration, or x, if you solve for x, is 1.3 times 10 to the minus 5 molar. 1.3 times 10 to the minus 5. So the molar solubility of silver chloride would equal 1.3 times 10 to the minus 5 molar in water, right? And so when you compare that, right, that's many orders of magnitude bigger, right? 4.7 times 10 to the minus 2 or 1.3 times 10 to the minus 5. Clearly, silver chloride is much more soluble in an ammonia solution than it is in water, okay? And that's really all we had for the day, just a quick sample showing you how to calculate the solubility of a complex ion in a solution that contains some of its ligand, right? Because that ligand pulls the solubility equilibrium farther to the right to dissolve more of that salt as one of the ions, the cation of that salt, gets more of the ligand bound to it, right? Based on Le Chatelier's principle, it pulls that reaction to the right, right? And we're going to stop right there. That's all we have for lecture material for today.
Professor?
Yes.
Is there a reason why we can't use the 5% rule during those calculations since it's a solid and it dissolves slightly?
In this one, yes. So in this one, if you actually look at the value for x, so x comes out to be, and it may vary somewhat, but in general, if you look at the x value on this, right, let me change my pen color here so I can distinguish. So when you say minus 2x, so you'd be in this case, it's not a big deal, but in some cases it might be depending upon the scenario, right? So this would be 0. What would it be? Almost 0.9, so 0.9, or sorry, almost 0.1, so 0.0958. And in this case, yeah, it's small compared to the original value here, but it's not always going to be the case, right? And so you can use that assumption if it checks out. but in general, even the math on this is still pretty easy to do that and just square. So you're going to get a better answer if you don't use that assumption on something like this. So long and short of it is, yeah, you could potentially, and it may not have a huge effect. But again, and a lot of the reason we use that 5% rule in acids and bases is because we're looking for a pH, and pH is on a logarithmic scale. And so a small change in concentration isn't a big change in pH. Okay?
Okay.
All righty.